Thanks to the organizers and to everyone in the room. Just a brief outline of my talk. I'm gonna pose a small fundamental question that I've been thinking about. It's related to quantum learning in the metrological sense. So first I'm gonna pose the question, then I'm gonna give us just a brief overview of what quantum metrology is. And then my question is actually phrased in terms of multiparameter learning. So I'm also gonna have to kind of have a slide on multiparameter stuff. And then when we've gone through that, I can get to the meat of my talk, which has to do with compressing or distilling a metrological information from quantum states. Okay. So what's the small fundamental question? This is it. So these circles here are quantum states, and we have many of them, and they each carry some information I. And the information I'm going to be talking about today is information in the kind of metrological sense. So what does that mean? So say that each of these circles is the state rho here, which is parameterized by two parameters, theta 1 and theta 2. And if we don't know these parameters, we might wish to learn them. So we want to do quantum learning. And then you take a bunch of these states and you measure them, and you do some clever kind of Bayesian inference or maximum likelihood estimation. And then you can find out what these unknown parameters are. So the question I want to ask is, given many copies of these states, can I filter them in some way so that I compress a lot of this information into just one state or into a few? And then I want to know how much information do I lose when I'm doing that. So that's the question. Why am I motivated in this? Well, I'm motivated by curiosity. I just wanted to know how much information a single quantum state can carry. But it's also useful for other stuff. So you can use this to mitigate detector saturation in many experimental scenarios. You can increase information per measurement rates. And you can use it to design smaller quantum memories. I'll touch on some of these points later in the talk. So we need just a little background on quantum metrology to understand what's going to go on here. So forgive me if this is familiar to many of you. But this is quantum metrology. So up here we have the kind of archetypical quantum metrology setup. We have something that creates a probe, rho 0. And then we have an experiment that depends on, in this case, just one parameter, theta, that we don't know. But we'd like to learn what theta is. It could be, a magnetic field, the strength of a gravitational field, or just, a polarization, rotation in an optical quantum computer. So you send in your probe states, and then you measure them. And when you measure them, you can have many outcomes. I call the outcomes small m, and they will occur with probability Pm of theta according to the Born rule. So if you repeat this experiment many times, you will start to kind of experimentally get the feel for what these probabilities are, and then you can use a clever method, like your favorite kind of inference method, in order to make a guess of what the unknown parameter theta is. So you make an estimate, theta e. And you might then wonder, how good is this metrological scheme? And then, the figure of merit for a single parameter is how large is the variance of your estimate. And if the variance is small, then, you have a good experiment for estimating theta. If the variance is large, your experiment is not that good. And there's this very nice, very old classical inequality called the Cramea-Rao bound, which binds the variance of the estimate in these kind of estimation schemes. And it's bounded such that the variance of the estimate is always greater than or equal to 1 over the number of times you've ran your experiment, or the number of probes you have, times this quantity I here, which is called the Fisher information. And the Fisher information is just a function of the probabilities of your experiment. And I'm going to be talking about the asymptotic limit today, where we do the experiment many times, n is large, and then this inequality becomes an equality if you're not doing bad things. So if you're a good person, then you get an equality, and then there are only two ways to kind of estimate better. So one way is to run the experiment more times, make n bigger, and the other way is to redo your experiment, maybe a new input state, maybe a new measurement, to make your Fisher information larger. So this slide is really just to kind of, this is what metrological information is about. You do an experiment, you get some probabilities. These are related to this Fisher information quantity. If that quantity is large, you get a lot of information per trial of your experiment. A natural question to ask, which Brownstein and Caves asked in 1994, was, if you do the best measurement, how much information do you get? So what they simply do is they take your Fisher information quantity, and then they maximize that over all possible quantum measurements you can do. And they find the following formula. So they call that the quantum Fisher information, but it's really just the Fisher information given the best measurement. That quantity is equal to the trace of your density matrix rho of theta times lambda squared. And lambda squared is something called the symmetric logarithmic derivative. And this thing is kind of nasty to calculate usually, at least when you have mixed states. What I'm talking about today, all of it is extendable. We've extended it to mixed states. But just to keep things simple, we're going to focus on the pure state scenario, where your quantum Fisher information takes a simpler form. It's just a formula like this. So you can plug in your pure state and you can calculate what it is. And then you know how well you can estimate theta. Okay, so that's quantum metrology. Now, this is what I'm interested in this talk. So we have some source of probes here. This is an artistic representation of my theory. So we have some probe source, a laser. It produces a high intensity beam of single photons. So obviously it's not super high because it's single photons, but today you can produce single photons, I think, about 1,000 times faster than you can measure them. So these single photons go and they hit something of interest. We want to learn theta 1, theta 2, theta 3 of something, and then the beam goes to a detector. But if this beam is too intense, your detector will saturate and you won't get any information. So what we're interested in is seeing if we can put in a filter here so that your detector only gets a weak intensity beam, but hopefully that weak intensity beam could carry a lot of the information that existed in the strong beam. And the slides before, where I showed you metrology, we only looked at one parameter. But in real experiments, you usually have many things that are unknown. So I really want to do this in the multiparameter regime. Here is a more schematic representation of it. We have an input state, a unitary that depends on a bunch of unknown things, and then we apply a filter. And only if outcome F happens, we send the state to a detector. So this brings me to this slides on multiparameter metrology, and then we can really get to the result of my work. So we saw that in single parameter metrology, you knew how good your experiment was by calculating the expected variance. And if that variance is small, then you know that this is a good experiment for measuring my unknown thing. And you could calculate how good it is by calculating the quantum Fisher information. But if you now care about many parameters, what's your figure of merit? Your variance turns into a covariance matrix, which tells you how well you managed to estimate all of the things that you're interested in. But it's a matrix, so it's a bit annoying as a figure of merit for how good your experiment was. So people that do kind of multi-parameter learning and metrology or quantum machine learning, they often introduce a scalar figure of merit called S. And S is just the trace of your covariance matrix multiplying a positive semi-definite weights matrix. And the most common weight matrix used in literature, both classical and quantum, is just the identity matrix. And then your scalar figure of merit is just the sum of all the variances of the unknown things. But you could have scenarios where, you know, one parameter is more important than another. So this is the thing we're going to care about when we're doing multiparameter learning, at least in this talk. And if you work on this for many, many years, as very clever people have done, you can come up with something that's similar to the Cramer-Rao inequality for quantum multiparameter learning. It's not quite as sharp, and there are more caveats. So this formula here applies again in the large n limit. And you have to be a bit more clever. But in principle, this is something you can get. So what does this tell us? The quantity S in the middle, that's our figure of merit, how well we learn the multiple parameters. And that's wedged in between like one thing and 2 times the same thing. So if we can make that one thing small, then we know that S will be small. So what is that one thing? Well, we have 1 over n, number of copies of the state, so number of times we ran the experiment. And then we have the trace of the same weight matrix times the inverse of something called the quantum Fisher information matrix. And I've given you the formula for the specific entries of this guy there. It's quite a tough thing to work with. For those of you who know this kind of stuff, it's 4 times the real part of the quantum geometric tensor. So if you can make that trace small, then you're going to push S to a small value. Okay, so what did we do with this in terms of this compressing of quantum information and distilling quantum information? Well, we added a filter, and then we wanted to know if we then look at the states that come out of this filter, how will S, our figure of merit, look for those states? So the first thing we had to do was to compute this quantum geometric tensor for a filtered quantum state. So I'm kind of sweeping a lot of calculations under the rug, but we get a really, really clean expression coming out in the end. So here we get 4 times the real part of this thing there, which is what we had before, but 2 differences. So now we get these factors of 1 over p, where p is the probability to pass the filter. And then between the inner products, we get f, which is the p of VM element that corresponds to a state that you're going to keep. So we have this formula. Now the question is, how do we pick f such that the states that come out of the filter have as much information as possible? This is what we're after. And it's a really, like, I was not very hopeful, because you can look at this formula here gives us just 1 entry of the quantum Fisher information matrix for these filtered states. So I can kind of sit around and I can play with f, and I can get something that gives me a small or a large entry at that point. But that will also affect other entries in the Fisher information matrix. So it seemed hard to kind of get something that worked. But then we kind of stumbled across something that just did work. So I'm not going to tell you how we stumbled across it. I'm just going to tell you what it is. And then we can talk about it later. So how do you choose an f that's really good? The way you do it is that you make an approximation of what rho of theta is. An educated guess, or someone who's measured a few of your million copies of rho of theta tells you rho of theta is roughly this. Or if you're looking for, if your rho of theta is a quantum image and you know roughly what the quantum image looks like, you could use that as your initial guess. And then you set your P of VM element to t squared, which is the transmission probability of your filter, times your guess of what rho of theta is, plus the identity matrix minus what your guess is. So that sounds like a strange thing. What does it correspond to? Physically, it corresponds to having a filter that if you are orthogonal to the state you expect, you always let that state through. But if a state comes in that's equal to the state that you expect to get, you only let it through with probability t squared. So it's kind of like an eclipse. So if we say that the moon is our filter, the moon on the sky will pretty much very well filter out exactly just the sun. They have the same kind of angular size on the sky. And only things that deviate a tiny, tiny bit from our estimate of what the sun is will be sent through. So this is kind of the POVM that you want to use for this filtering. Often you have to design that POVM in an iterative fashion, but the kind of limits work out in your advantage. So that's the POVM you want to use. And how much time do I have? 3 minutes, okay. Well, you take that POVM and then you kind of get to work. So you start kind of evaluating things. And yeah, I will just say that the limits and error scalings of things really work in your advantage for this POVM. So at the end, if we look at one specific element of the quantum Fisher information matrix, if we compare the quantum Fisher information matrix entry of the states that come out of the filter with the ones that go into the filter, they've been boosted by this 1 over t squared, and t squared was our transmission probability. So if that's small, then we boost this entry of the Fisher information matrix. And this f here didn't depend on which entry I wanted to boost. So in fact, this f is going to boost all of these entries uniformly. So if we go back to this inequality of our scalar variable, we'll see that when we apply this filter, we're going to shrink the entire quantum Fisher information matrix by a factor of t squared. And so we're also, we're going to increase our entire Fisher information matrix by a factor of t squared. So we're going to shrink our figure of merit by a factor of t squared. So doing this, and in our paper we show that there's no cap on t squared. You can essentially push in as much metrological information as you want into one state, and it's lossless. So if you take the quantum Fisher information matrix of the states that come out of the filter and you multiply that with the probability of coming out, you get back exactly the initial information. So just to summarize, so what we've shown in a number of papers is that you can have a bunch of particles with metrological information. You can do a clever thing that pushes all of their information into just one or a few particles without any loss. So that's the kind of take-home message. We published a bunch of papers on various things with this. I'll just probably mention that the most exciting thing we had out recently was with Ephraim and two of his very talented students, Noah and Batuhan. And I think, Batuhan, you have a poster of the single parameter experimental realization of this information compression out here. So with that, thanks for listening.
Very interesting.